Thank you so much for the introduction and for the invitation. It's really a pleasure to give this talk. And so what I'm gonna talk about is some of the recent results from my group about network games when we have very large populations. And so let me start with a very kind of broad motivation. So why are we interested in network game? Well, that comes from the observation that in many socio-economic settings, we have that individuals make decisions, but they are not making this decision in isolation. They are actually affected by the decision and action of their friends, colleagues, peers, or competitors. And we can typically model this network of interaction with an underlying network. And there are many examples of this type of setting, spanning from adoption of innovation and behavior, opinion formation, social learning, as well as maybe more in economic setting, public good provision, or competition among firms. Now, it's clear that being able to understand what is the overall outcome produced by this individual behavior in network environments has fundamental implications for regulation and policy making if our objective is to possibly maximize system performance or profit or like agents' welfare. Now, a very powerful framework that has emerged in the last decade or so to model this type of strategic behavior in network setting is the framework of network game, which is going to be the main topic or the main framework that I'm going to use throughout the talk today. So just to set the base, what I'm going to define a network game is a game where I have n agents. These agents are interacting in some heterogeneous way, and I'm going to represent this interaction with a network. And the adjacency matrix of this network is going to be a matrix G, where the element in position ij is going to tell me whether agent J has some influence on agent I or not. And the objective of every agent is to select a strategy, which I'm going to denote by xi, from some feasible set, calligraphic X, in order to minimize a cost function. And now what makes this a game is that this cost function does not depend only on the strategy of agent I, xi, and possibly some local heterogeneity parameter theta I, but it also depends on strategy of other agents. And in particular, what makes this a network game is that I can summarize this effect of other agents on a specific agent I by this magenta quantity, zi of x, which is what I'm going to call the local aggregate, because this is just the sum over all my agents of their strategies, weighted, however, by the local weights given by the underlying network. So this is now a quantity that is going to be different for each one of my agents and basically depends on their neighbors. Now, clearly, we are in a game theoretical setting, so the concept of outcome that we're going to focus on is the one of Nash equilibrium. I'm sure, like in this audience, everybody knows what it is. Just to set notation, I'm going to denote this by x bar. This is a set of strategy where no agent has any interest in unilateral deviations. Perfect. So the framework of network game, as I mentioned, has been introduced, I would say, 10, 15 years ago. So there's been a lot of work and a lot of interest in understanding this setting. And most of this work, however, focused in setting, as I just described, where the underlying network of interaction is fixed, and it's actually known to the planner. Instead, what I'm going to discuss today is like an extension of this setting where we are actually considering very large networks. So think of application where I can have thousands of agents. And what I'm going to argue is that in this case, actually two problems may emerge. So the first problem is that from the point of view of a planner, somebody that wants to intervene on the system, it's probably not very accurate to assume that this planner has exact information about how the agents are interacting. So in reality, probably doesn't even know what the underlying network of interaction is. And the second type of problem, more from the perspective of the agents, is that if my network is very, very large, it's typically unreasonable to assume that this is actually going to be fixed. In fact, what's probably going to happen if agents interact repeatedly in time is that the network of interaction may change slightly from each repetition to the next one. And in fact, even the population itself may change with agents that may come and go and leave the system. And so really what kind of the underlying question that I've been addressing the past couple of years is how can we kind of still understand and analyze strategic behavior when we are in this large network setting, when we have these kind of new challenges. And kind of the key observation that I'm going to build throughout this talk is that while it's true that having an exact description of network interaction is probably unrealistic, what one can still get is a probabilistic description of how agents are interacting with each other, which can be used to infer a stochastic network formation model. And so throughout this talk, I will basically go from a deterministic approach where analysis and intervention are based on exact network data to a stochastic approach, where instead I'm going to assume that there is an underlying stochastic network formation model from which different networks can be realized. And basically what I'm going to focus on is therefore this concept of sample network games, which is a network game exactly as I described before, but now played over a network that is not fixed, but is sampled from this underlying stochastic network formation model. And in the rest of the talk, I'm actually going to use kind of this general idea or the general framework to kind of answer the two questions that I posed before. So in the first part, we're going to see whether having statistical information, having information about the stochastic network formation model is enough for the central planner to kind of predict and regulate strategic behavior in any of these sample network game. And then in the second part, instead taking the perspective of the agents, I'm going to try to see what happens if we think that we are in this setting where agents take part to this game repeatedly in time. But now at every repetition, I'm going to have a different sample network, mimicking this time variability that I have in large network setting. And I'm going to try to ask question of how can agents learn when we have this type of time variability, such that every time they take part in the game, the network is slightly different, so the game is slightly different. Okay, so having said that, kind of this was a general overview. Let me go to the first part. And again, here the main question is, from the point of view of the central planner, how can he understand what is going to be the equilibrium action of the players in this large network setting when it doesn't have network information, and in particular, if he only has some statistical information, is this enough to predict behavior? And this is some work that I've done together with a PhD student in my group, Kiran Rokade. And maybe the first thing that I need to do in order to be a little bit more specific about this work is to tell you what type of stochastic network model we're going to use. And in this case, what we're going to use is the concept of graphon. So what a graphon is just a symmetric measurable function, W, that takes value in the 0-1 square interval and maps that into 0-1. And why are graphon interesting in the concept of network theory, where there's actually two ways in which you can interpret a graphon in relation to network theory. So the first way, maybe the more classic way, is as a limit of a graph. So the idea is that think of that you have network with increasing number of nodes. And now suppose that this number of nodes goes to infinity, such that in the limit, you can map that into a continuum mapped in 0-1. Then what the graphon is a model that tells you what is the level of interaction between two infinitesimal agents, U and V, among these 0-1 population. There is, however, a second way in which you can think of graphons in relation to network, which is as stochastic network formation models. And this is kind of what I'm going to use throughout the talk today. So the idea is basically you can use a graphon to generate random graph. So that's how we're going to sample graphs basically from this stochastic network formation model. And the way you do that is actually quite simple. So say that you want to create a network with 5 agents, that what you can do is you can assign a label to each one of your agents in 0-1, and this can be done randomly. And then for every pair of agents, you can connect them with Bernoulli probability coming from your graphon evaluated at the corresponding label. And then you can repeat this for every pair of nodes in your network, and you see you're going to get one random realization. And this is actually a quite powerful way to generate a random graph. That's why we kind of decided to work with graphons. Because, for example, it generalizes Erdős-Renyi model, where you connect every agent with same probability. That would give a constant graphon. But also more richer, maybe community structure like the stochastic block model, where agents are divided into communities, and you connect them with probability that depends only on the community they belong to. This, again, can be captured with a graphon, which is now going to be piecewise constant. And here I put some reference to the kind of the general theory of graphon, as well as different application that this theory has found in different areas. So what I'm going to do in this first part of the talk is show you one application of this graphon theory to the set of network games. And then we're going to see how can we use that to understand behavior in very large populations. Okay, so in order to do that, the first thing that we do, again, what we're interested in is understanding behavior for large population. So our first idea was, let's take that to the limit, and let's see whether we can construct a model of how strategic interaction happens for an infinite population. And note that this is a concept that is not new, of course, that's been used, for example, in min-field games. The main difference here is that we want to maintain heterogeneity between the interaction among the agents, and the way we're going to do this is through the graphon. And so basically what we did was to define this concept of graphon game, which is pretty much a one-to-one extension of the setup of network game that I've just introduced, where kind of the main difference is that instead of looking at a finite population, we're now going to look at a continuum of agents that we assume map in 0, 1. And then exactly as before, every agent wants to select a strategy to minimize a cost function. The only thing that's going to be different is how we compute the local aggregate. So if you remember before, there was a sum over all my agents of their strategies weighted by the parameters coming from the underlying network. Now I have a continuum of agents, so this is going to become an integral, again, of the strategy of the other agents, and I'm going to use as weights the weight coming from the graphon model, and this is the way I'm going to capture, again, heterogeneity among my agents. Now, having said that, basically we have, again, a game setting, so again, we can define a concept of equilibrium. The only thing to be slightly careful here is that my equilibrium is now going to be a function because I have a continuum of agents. So this is something that tells me for every agent in 0, 1, what is the corresponding strategy. But for the rest, the concept of equilibrium is the one that we are all very familiar with. So again, a function here is going to be a Nash equilibrium if no agent has any interest in unilateral deviation. And having set up this framework, I guess there are some key questions that one can try to ask. So the first is, well, we've introduced this notion of equilibrium, but does it even exist now that we are in this infinite population? And if so, what property does this equilibrium has? And then the second and probably most important question is, what is the relation between this game that we define for infinite population to the game over large networks that we started from? And this is something that I've been studied for the past few years. And in fact, a first set of answer to this question was obtaining this paper here that I did with my postdoc advisor, where we kind of answered this question for the class of smooth convex game under the assumption of having a unique equilibrium for this game. And in fact, what we show in that case is that, yes, you can prove existence of the graphon equilibrium, and this graphon equilibrium is actually predictive of behavior in large sample network games. And what do I mean by this exactly is that if I take my graphon, I sample network from it, and then I look at what is the equilibrium that I have for each one of the game over the sample network, as long as my population is large enough, this equilibrium is going to be well predicted by the equilibrium that I have for the infinite population. And in fact, you can make this argument very rigorous and show that there is convergence of the sequence of equilibrium sample network to the equilibrium of the graphon game as the population size increases. And again, I will not go through this in this talk, but I refer you to this paper here if you're interested in that. What I want to present you in this first part of the talk is some extension of this work, where we started investigating kind of the similar question, but when we don't have uniqueness of the equilibrium. So we wanted to kind of generalize this set of results for a larger class of games that did not restrict to uniqueness. And so the first question, as I mentioned, that you can ask is, what about existence? Like, are we even sure, like, what type of assumption do we need to set up in order to make sure that at least we have existence of the equilibrium in such graphon games? So again, for the infinite population. And so what we are going to assume is, first of all, that we have continuous game. So I'm going to assume that the strategy set is compact and that the cost function are continuous in all their arguments. Now, unfortunately, so far we have not been able to show that this is enough to guarantee existence of the equilibrium. I think this is still an open question. We also were not able to find a counterexample, so there is some hope that this is true. But what we were able to show is additional set of assumptions that you can add on top of this to guarantee existence. And in particular, we actually look at two different sets of complementary assumptions. So one is convexity, and I guess this should not come too much of a surprise for people that are working with games. So the first step of assumption is that the set should be convex, the strategy set should be convex, and the cost function should be quasi-convex in own strategy. And then, however, we also found another set of assumptions that we can add to the continuity in order to still guarantee existence. And this is obtained by kind of restricting the type of interaction that we can allow to so-called finite type games. And what do I mean by this is that basically our graphon has a stochastic block model structure that I mentioned at the beginning, encoding this concept of community. So this is kind of just to make things clear, an example of such a graphon where I have two communities. And this you see is what I was saying before, that the graphon is piecewise constant, because basically the connection, the strength of interaction between agents only depends on community. So I have some value for interaction between community 1, some for between 1 and 2, and so forth. And then if we have this type of block model structure, as well as the same type of structure for the cost function, so for the heterogeneity, then we're also able to show that this is enough to get existence. And so really the kind of the overall picture that we have at the moment for existence of graphon game equilibria is that if we have continuous game and either finite type games or convex game, we can guarantee existence. And so what I want to do now is give you a little bit of insights on the proof of these two results to kind of show you how this can be obtained. And so let me start with the first one, so like a kind of convexity. And so here, like our first proposition is to show that if I have a continuous and convex graphon game, then this game will have a Nash equilibrium. And the idea here is actually quite standard. It follows fixed point arguments that were made already in 73 by Schneider for non-atomic games. Again, the big challenge here is that we have continuum of agents. And the way we did this is basically following the same line for graphon games, is to first of all define a set, which is the strategy profile set, which you should think as the set of all basically functions that are feasible strategy profile, meaning that for every agent U, the strategy that I'm selecting actually belongs to the strategy set. And then based on this strategy set, we can define so-called best response mapping that tells me basically what is the set of possible best responses of the agent to some strategy profile X. And what do I mean by that is that the strategy profile X is going to induce some local aggregate Z, and then I'm going to look at the set of all possible best responses for each agent U to the cost function evaluated with that local aggregate. And then this is kind of the point-wise response for each one of my agents, and then I can look at all the functions that satisfy this constraint. And again, the challenge here is that when we're working with non-uniqueness, this is a correspondence, it's not going to be a map. So for a fixed strategy profile, I may have multiple best responses. Okay, and the idea, I guess this is well known, is that if I can find a fixed point of this best correspondence, this is actually going to be a Nash equilibrium of my game. So really what I really want to do is to prove that this best response correspondent has a fixed point. And the way we're going to do this is by applying Kakutani-van Glicksberg theorem. And in order to do that, we actually need three main properties. And so this is basically what we show in the paper. So the first one is that the set X of the strategy profile should be non-empty, which is pretty obvious. It should be convex, and this comes from the convexity assumption. As long as my set X is convex, this set of strategy profile is going to be convex. And then the third thing that we're going to need is compactness. The only caveat in this proof is that unfortunately, since we have an infinite dimensional space, we cannot prove compactness in the norm topology, but we have to use the weak topology to do that. But it turns out that we do have weakly compactness. So this is something that we can do as long as we work with the weak topology. The second main thing that we need to apply this theorem is that my best response mapping when evaluated for some strategy profile X should be non-empty and convex. And this is something that, again, we can guarantee. It follows quite easily from the fact that we assume this is a convex thing. So in particular, the cost function J is quasi-convex. And then finally, the third part, which was actually the maybe trickiest one to prove, is that we need to prove that the best response correspondent has a closed graph, again, in this weak topology, because here we have weak compactness. And so just to give you an insight of how we do this, basically what you need to prove is that the best response correspondent has a closed graph in this weak topology. So what does that mean? It means that if I take a sequence of point xk prime belonging to the best response correspondence evaluated at xk, and I have with convergence of xk prime to x prime and xk to x, then I should be able to prove that x prime also belongs to the best respondents to x. And the way we prove this result, and again, the main idea here were from the Schneider paper, is by contradiction. So, and basically what we're going to do is build on three main facts that are reported here in the slides. So the first fact is that if X prime does not belong to the best response, so this is kind of our contradiction step, then because this is convex, by Hahn-Banach separation theorem, I can find a function f such that basically I can separate the inner product between f and any point in my best response set from the inner product between f and the point x prime that does not belong to the set. And so I can find this function f such that the sup here is going to be strictly less than the value that I would get with x prime. Then the second main thing that we are going to use is that Berg's maximum theorem guarantees that if I look at the best response to strategy profile X of agent U, this has a closed graph. And then the third fact is that since I have with convergence of xk prime to x prime, by real definition of with convergence, I know that the limit of the inner product of my f with xk prime is equal to the inner product of f with x prime. And this is something I'm going to call Q here. And with this treaty set in place, then it's pretty easy to show that I have a contradiction by using a result by Oman on like integrals. And so in particular, remember Q here is defined as the limit over K of this integral. Now, I cannot bring the limit inside because here I only have weak convergence of xk prime, right? Xk prime may not converge to anything. But this result of Oman tells us that this limit here is going to be contained in a set, which is computed as all the integrals of f times some function r, where r is defined pointwise as the limit of xk prime. And again, this limit now is done pointwise. And then the next step, I'm sorry, my cursor, I guess, is on the way here, but is to show that since the best response set here is closed, the limit point are going to be best responses pointwise for each agent. But then if they are best responses pointwise for each agent, the entire function r is going to belong to the best response set. And this is the last step, because by property 1, I know that as long as r is in the best response set, this integral is going to be less than q. So each element in this set that I have here is going to be less than q. And this is a contradiction because I know that q was a point in that set. And so this is kind of by contradiction, shows that this has a closed graph. And then I can use basically my Kakutani-Van-Glinsberg theorem to make sure that I have a fixed point. Okay, and so this is how basically I can use convexity to make sure that I have existence. And then, as I mentioned, there is another side of the result where I can actually prove existence without the need of convexity. And this is something that we found quite interesting, as long as I work with graphon that are of this finite type form. And again, this is something that we tried for a while, and we were a bit stuck because we were trying to prove it following the same recipe as before, starting from the set of strategy profiles. And it turns out that in that way, we were not able to find a solution. But at some point, we decided, well, why don't we look at the set of local aggregates instead of a set of strategy profiles and try to work and find a fixed point in that set. And so here, what I'm defining by Z is the set of all functions that can be obtained as local aggregates induced by some miscible strategy profile. And what is the advantage of working with that is that we were able to prove that this set is non-empty and compact, but most importantly, it's convex. So even if my set of allowable strategies for the agent is not convex, once I take the local aggregate, this will become convex. And this is kind of the way we work around the fact that we don't have convexity to begin with in the cost function and constraint set, but we really use this property of the fact that we are taking an integral. So we're really exploiting properties of graphon games. And kind of to give you a intuition of why we get convexity in this case, so remember, how do we compute the local aggregate for a certain agent U? That's just going to be the integral of W, UV, XV in DV. And now remember that we have this finite type abstraction. So this WUV, think of it would be just a line here. Like if I fix U, this is an integral in V. So when I take like this integral, I'm not going to have all different values. I'm going to have something that is piecewise constant. And so I can actually split this integral in a summation where I have as many terms as community, and really what I'm going to have is the value of interaction for that community L, and then the integral of the strategies across that community. And why is that useful? Because then if I want to see what is the convex combination between two local aggregates, I can rewrite that using the summation as something that depends on a convex combination of integrals. And this is something that, again, is a result by Oman that we are using here, that the set of integrals of a correspondence is a convex set. And so even though this set calligraphic X is not convex to begin with, the set of integral is going to become convex set. And so what this means is that we can find X3 such that this convex combination of integrals that I have in this term here can be expressed as a new integral of this function X3. This is within each community. I can then piece that together for each community to find an entire strategy profile that will give me that the convex combination of local aggregate is a local aggregate itself, and this will guarantee that I have a convex set. And then basically once we have this in place, then we can define again a best response correspondence that will now map local aggregates to local aggregates. And again, we can use similar arguments as I've done in the proofs before, not going through all of them again, but to guarantee that we have a fixed point in the local aggregate, and this fixed point in the local aggregate will induce an equilibrium in the strategy profile. Okay, perfect. So I guess if you have any questions, just feel free to interrupt me. So this was just the first result that I wanted to present about existence of the Nash equilibrium. And for graphon games. So far what we've analyzed, it's only what happens for the infinite population. Now, the next question that you can ask is, this is all nice, but is it at all informative about what's happening for finite networks? So for networks where I have a finite number of agents and they are interacting according to a network sample from the graphon. And again, this is a question that we asked in the case of unique equilibria. In that case, the relation was very clear, like every sequence of equilibria and sample network was converging to the unique graphon equilibrium. But you see, once I have non-uniqueness, this is a little bit more of complicated question to answer, because I have a set of equilibria for each network game, and I have a set of equilibria for my limiting graphon game. And so really what I'm gonna try to address now is what is the relation when we are in this non-unique setting. And the first thing that I have to a little bit specify is if I want to kind of compare, which is what I'm gonna do, equilibria in sample network games with equilibria in graphon games, I need to be a little careful, right? Because I mentioned in graphon games, equilibria are functions, while in sample network games, they are vectors. So it's a little bit hard to compare this object. And so instead of doing that, what we're gonna do is to, instead of considering a sample network game, construct an auxiliary graphon game where I have that all equilibria of this new graphon game are actually in correspondence with the equilibria of the original sample network. And the way we're gonna do this is basically if I have a finite network, I can always construct a graphon, which is piecewise constant, where basically each piece here is gonna correspond to a link in the finite network. And so instead of looking at equilibria in this game here, I'm gonna look at equilibria in this graphon game here. And again, what we show is that for any equilibrium that you have in the sample network, that's gonna be a corresponding equilibrium in this auxiliary graphon game. Okay, so with that in place, our first result is to show that if I can find a sequence of equilibria in the sample network games that's convergent, then the limit should be a graphon equilibrium. So if I have kind of some limiting behavior in the finite population, they will converge to an equilibrium behavior for the infinite population. And the main idea to prove this result is, again, to use this argument with best response correspondence. And I'm now going to see this best response mapping both as a function of the strategy X, as I was doing before, but also of the graphon. And why is that? Because, again, I want to compare my real graphon game, which is graphon W, and so for which equilibria are going to be fixed point of this best response mapping here, to equilibria in sample network game, which I'm going to see as equilibria in this auxiliary graphon game, which has this piecewise graphon that I'm calling here Wn. So that basically using this best response correspondence, I can characterize both graphon equilibria and network equilibria as fixed point of this best response correspondence, just in one case with respect to the original graphon W, in the sample network with respect to the empirical or like piecewise constant graphon Wn. And then our result to kind of show this type of convergence is to rely on the fact that it's actually known from results by Lovas and graphon theory that Wn, this empirical graphon, will converge to the true graphon W as the population size increases. And then we also proved that the best response correspondent, now as seen as a function of both X and W, has a closed graph. And then this will immediately imply that if I have a sequence Xn that's converging to some X star, that will X star needs to be a fixed point of the limit here, and therefore a graphon equilibrium. So this is kind of nice. It gives us, like, if I have a convergent sequence of equilibria, this will converge to a graphon equilibrium. Now, of course, the other thing that you can ask is, what about the vice versa? So if I take a graphon game equilibrium in my limiting population, is it always true that that's going to be the limit of Nash equilibria in finite networks? And it turns out that actually the answer to that second question is no, when you don't have the uniqueness. And to see that, let me go through a very quick example. So what I have here is a simple game where I only have two communities. And the objective of every agent is basically to copy 2 times the local average of the other community. So here's the type of interaction is very simple. Intra-community 0, extra-community between community 1 and community 2 is 1. So that really the local average is going to be the average of what the other community is doing. Now, it's clear that in these games, since all my agents here are actually homogeneous, all agents in the same community will end up playing the same strategy at equilibrium. So I can just denote by x1 the strategy played by agents in community 1, and x2 the strategy played by agents in community 2. And again, the objective of every agent is to copy 2 times the local aggregate. So for a condition for equilibrium in the infinite population is going to be that x1 should be equal to 2 times z1. But for how I define community interactions, z1 is just going to be x2 times the mass of agents that I have in community 2, which is just 1/2. So this condition will become x1 equal to x2. So this is a very simple graphon game, basically, in which as long as all the agents play the same strategy, no matter what the strategy is, that is going to be an equilibrium. So here I have an infinite number of equilibria for my graphon game, which is all agents play the same strategy. Now let's see what happens if I now look at games where the network has been sampled from this model here. So now I'm looking at sample network games. And again, the condition here is still going to be the same. So I want x1 for each agent in community 1 to be equal to 2 times the local aggregate. But what is the local aggregate going to be now? This is going to be x2 played by community 2, again, times the fraction of agents that I have in community 2. And this is now going to be something random, right? Because it depends on the assignment of labels that I have for my agents. So this is something that I'm going to call alpha n. And so here the condition for equilibrium becomes that x1 should be equal to 2 times alpha n x2. And then if I write the same condition for agent 2, I will get this one here. And now you see that depending on what alpha n is, I may have a different set of equilibria. Specifically, if alpha n is exactly equal to 1/2, I'm back to the previous case where as long as agents adopt the same strategy, everything is an equilibrium. But if alpha n is different than 1/2, then the only solution to these two equations is that 0-0 solution. So all agents should play 0. And the key point of this argument is that with probability 1, when I'm sampling my networks, I'm actually not going to split the agent exactly equally in the two communities. So infinitely often, I will have that alpha n is different than 1/2, and then my only equilibrium is 0-0. And then you see if that's the case, there are equilibria in my graphon game, basically any equilibria which is not 0-0, for which I cannot find a sequence of exact Nash equilibria converging to it, because in sample network games, infinitely often, the strategy profile is actually going to be 0-0 is going to be the only equilibrium. So this was a kind of like a special example that shows that there can be graphon equilibria that are not limit of equilibria in the sample networks. So this was a little bit puzzling, but what we kind of were able to show is an approximate converse that says that for any graphon equilibrium, I can actually find a sequence of approximate Nash equilibria converging to it. And in fact, this approximation, the epsilon, can be as small as desired. And the proof for this is actually constructive. So the way we prove this is to use the graphon equilibrium as a way to construct a strategy for the sample network. And the way we do this is just by, remember, each agent in the sample network has a label associated with it. So we can just assign a strategy to this agent as the graphon equilibrium strategy evaluated at that label. And this is going to give us basically a piecewise constant strategy where each piece here is the strategy that the agents are going to take in the sample network. And then it's easy to show that as the population size increases, this piecewise constant approximation actually converge to the graphon game equilibrium. So this is a set of strategy profiles that will converge to the graphon equilibrium. And the second step that we can show is that this is actually an epsilon Nash equilibrium of the sample network game. And so we can constructively find a sequence of Nash equilibria that will converge to a graphon equilibrium as long as we allow kind of approximate Nash equilibria, so epsilon error. And again, this epsilon can be made as small as you want, as long as you take larger and larger population, because you're making this approximation better and better. Okay, perfect. So this is kind of the summary of part one. So basically what we've shown in the case of non-uniqueness is that we don't have this very simple convergence result as we had in the unique case, but still we can find a relation basically between the set of equilibria for the graphon game, so for the infinite population, and the set of equilibria, exact equilibria for a sample network game, as well as the set of approximate Nash equilibria. Okay, so this is kind of the end of part one. So if you have any question, I'll be happy to answer those. Otherwise, I'm gonna go to the second part, and there we're gonna switch a little bit perspective, and instead we're gonna think about agents more than like planner and what the planner can do, just knowing statistical information. Okay, so let me go to the second part. And in this case, again, this is some work that I've done together with Kiran Rokade, as well as Feras Altar. These are both PhD students in my group. And here, the question that we're going to try to address is, can we still use this idea of network sample from an underlying stochastic network formation model to study how agents learn in dynamic network environments? And before going to our main result, let me, of course, say that the topic of learning in games has been addressed by many, many works. And of course, this list of paper that it's here is not at all comprehensive, but I want to just give you a kind of flavor of the type of results that people have been investigating. So starting from learning in static games, again, this has been a large literature on that look at different type of dynamics that agent can take to kind of learn the Nash equilibrium while taking part in repetition of the same game over and over in time. And again, the main difference between this large class of works and what we're going to focus on today is that we're going to assume that instead agents still take a repetition of over time, still participate in different repetition over time of this game, but now the game can be changing in time. So basically the way the game is going to change for us is that the network of interaction is going to change at every instance. And so as a result of that, for example, the Nash equilibrium set is going to change at every instant. Now, cases or dynamics where there is a network between agent that's changing in time is also another area that's been studied a lot in control and distributed optimization. And people have looked at, for example, consensus schemes under time-varying communication among the agents, as well as distributed optimization scheme, as well as distributed Nash equilibrium seeking. But in all this work, what was changing was the way agents were communicating with each other, but not the underlying problem. So for example, think of it distributed optimization. There is one optimization problem agents are trying to solve, but they are trying to solve communicating one with each other, and this network of communication changes in time, but the optimization problem doesn't change. And so this is the kind of the main difference from what we are doing, where instead the problem that agents are trying to solve, in this case, find an equilibrium of a game, is actually changing in time because the game itself is changing at every time. So it's kind of the network of interaction which enters in the cost function that's changing, not the network of communication among the agents. And then finally, maybe this is like the set of results that is closer to what I'm going to talk about today. People have looked at what happens when I have time varying setting, exactly as I mentioned right now, and in particular, what happens with dynamic population. So there is this recent literature on so-called open multi-agent systems that look at different problems, spanning from consensus, resource allocation, or gradient schemes, where they look at kind of these classic questions, but under the assumption that now not all agents are always present, but agents may leave the system and may come at different time. And as well, time variability has been studied for games with specific structure, like congestion game, markets, or auction. So kind of the main difference that between this last set of results and what I'm going to talk about today is that what we're going to talk about is specific to the set work of network games, as I've introduced at the very beginning of this talk. And in particular, we're going to focus for the second part. This is actually very recent work. So far, we work out the linear quadratic game case. So that's the case that I'm going to present today. So to make things a little bit more concrete, let me specialize the network game model, the general model that I presented before, to the linear quadratic structure. And in fact, to make things even simpler, I'm going to focus on so-called scalar strategies, so that the set here is R instead of Rn, but this is easy to generalize. It's just for simplicity of presentation. And so what is the main assumption in linear quadratic game is that my cost function is not any generic convex function, but it's actually quadratic in own strategy and linear in the local aggregate. So that it has this nice structure that you can think of decomposing two terms, one which represent kind of the cost associated to selecting action xi, and one that is the return for that action, where importantly, the marginal return depends on the local aggregate, thus again, coupling the behavior of different agents. And what we're gonna assume here is that I have a smooth and convex game. So in this case, we're gonna work under the convexity assumption. So what that means is that this qi term here for linear quadratic game is positive, so that this is a convex function, and my set xi that I'm gonna assume for each one of the agents is compact and convex. Okay, and again, the main question that we're gonna try to answer in the second part of the question is how do agents learn equilibria in this type of setting using distributed communication with their neighbors? And this is a question that in the static setting, when the network is fixed, is of course been studied and well known. So let me do a very quick recap on what is known in that setting, and then I will present our result for the time varying case. And in order to introduce this result, I have to introduce a second reformulation of equilibrium.
Sorry, Francesca, I have a question. Here, what are the agents trying to learn?
Well, that's a good question. In the time varying setting is not even clear, right? Like if the network is fixed, what they are trying to learn is the Nash equilibrium of the underlying game. If the network keeps changing, the network Nash equilibrium keeps changing. So we're gonna see in a moment what they are gonna learn. But yeah, it's not even well defined what they are trying to learn when we are in this time varying network setting. Thank you for the specification. Okay. So to first of all do the recap in the case of static setting, I'm going to introduce this reformulation of equilibria in terms of solution to variational inequality. So in the first part of the talk, we saw a reformulation of equilibrium in terms of best response of a mapping. Now we're going to see a different reformulation in terms of solution to a VI problem. And for those of you who have not seen VI problem, this is just some mathematical object that depends on a set X and an operator F. And we say that a vector X bar solves this VI if and only if this inner product is positive for all point X in the set. And why are these interested in game theory? Because it's well known that a vector X bar is a Nash equilibrium of my game if and only if it solves a specific VI, where the set is obtained as the Cartesian product of the local strategy set of all my agents. And the operator F of the VI is the so-called game Jacobian, which is obtained by stacking one on top of each other, the gradient of the cost function of each player with respect to its own strategy. And so the way you see this is basically by writing first order condition for each one of the problem of the agents, and you can prove that under convexity, these two reformulations are equivalent. And why is it interesting using this reformulation? Because then we see that properties of equilibria can be inferred from properties of the corresponding VI. And in particular, one property that people have used a lot is strong monotonicity of the game Jacobian, which is defined here. And this is something that we're going to do and assume in the rest of the talk today. So we're going to assume that we do have this strong monotonicity. And in fact, in this previous paper of ours, we look at what are sufficient conditions on the network and the cost function that would guarantee that the game Jacobian of a network game is strongly monotone. And this is kind of how this condition looks for the linear quadratic game that we're looking at right now. And so again, why is this strong monotonicity interesting? Well, first of all, because if my operator is strongly monotone, then I can guarantee existence and uniqueness of the solution of the VI, and therefore existence and uniqueness of the Nash equilibrium. So in this setting, under this assumption, we're going to have uniqueness. The second thing is that you can use that to study learning dynamics. And in particular, one class of learning dynamic that people have focused on is so-called projected gradient dynamics, where each agent updates iteratively in time its strategy by taking a projection of the previous strategy minus a step in the direction of the gradient. And this gradient is computed according to the network, which in this case is fixed. And why is that related at all with the VI? Because this gradient operator here, you see, is just the ith component of the game Jacobian. So in compact form, you can rewrite this projected gradient dynamics as this scheme here, which is now can be seen just as a scheme to compute the solution of a variational inequality. And it's well known from VI theory that as long as you select your step size small enough related to properties of the F operator, this will converge to a solution of the VI, which in our setting is a Nash equilibrium. So this is how you kind of can prove convergence of projected gradient dynamics in network games where the network is fixed. So what is the part that very quickly, because I'm running out of time, what I kind of mentioned here is what happens if instead of looking at setting whether network is fixed, we now assume that the network may change at every iteration. So at every iteration k, I have a different network, which means I will have a different game. And here I have a very quick motivating example of why can I have this type of network variability structure, which is related to an online market where I have n sellers. And the objective of every seller is to select at which price to sell their product. So xi here is going to be the price of product I. And the variability in this type of example comes from the fact that every day I may have different customers showing up to these online markets. And this customer may have slightly different preference for the products that are sold. And in particular, I can put a formula for what is the demand that a certain customer C has for product I at repetition k of my game. And this is going to be some fixed demand minus something that depends on the price. Again, this is to model the fact that higher the price, the lower is going to be the demand. But crucially, this price is going to depend on the price of product I, as well as price of complementary products. And the level of complementarity is something that may be specific to customer and may change from day to day. So that typically this level of complementarity between product I and J is kind of can be modeled as a realization of a Bernoulli random variable, where this G bar Ij is kind of the likelihood that I and J will be complementary. And this is the demand for each one of my customer. If I want to see what is the profit of the seller, I have to aggregate all these demands. And you see, without going too much in the detail, once I do that, I will have that the complementarity between product I and J, once I sum overall the customer, is going to be a random variable, and which will depend on the realization of the customers that I have every day. So this is going to give me some variability that of how different products in this case interact, which is going to be different every day. Okay, so what is our main result in this area? Well, is to study what happens if agent takes gradient dynamics, as we kind of introduced before, but we're now in this time varying setting. So here is kind of the gradient dynamics in compact form, exactly as we've seen before, with two main modifications. So the first one is that GK is now not fixed, but depends on the realization of interaction that I have that day. And the second one modification that we did is to allow for time varying step sizes. This is something that we need in order to prove convergent. It's actually something that's been used before in the literature. And we're going to make classic assumption on that the sum of the tau k is infinite, but they are square summable. And then under this assumption, and this is kind of the main result and also answered the question that I had before, what we were able to show is that the strategy profile does still converge to some vector x bar. So we do have that agents are learning something, so their strategies are converging almost surely. And the interesting part is that what they are learning is actually a Nash equilibrium of the game played over the expected network. So again, every day here, networks are sampled from an underlying stochastic model. What agents are learning in this setting is the equilibrium with respect to the expected network. And the way we prove this result is actually by reformulating these gradient dynamics that I had here, which again depends on the time varying network, as gradient dynamics around the expected network plus some noise term. And then we can use known result basically of convergence of gradient schemes for variational inequalities when I have some additional noise terms. And so the whole idea of this proof is to verify that the noise that we have for our specific dynamics satisfies these assumptions that are needed in order to guarantee convergence to the solution of this VI. And this VI, again, is the VI with respect to the expected network, and that's why we are converging to the Nash equilibrium over the expected network. And then, of course, the next question that you can ask is, well, it's nice, agents are learning this strategy over the equilibrium over the expected network, but how is this performing with respect to the stage game, right? Every day they're actually playing with respect to a different network realization. So is this strategy any good? And here, using kind of similar ideas as in the first part of the talk, what you can prove is that this strategy that they are learning is actually an epsilon Nash equilibrium for any stage game, where this epsilon goes to 0 as long as the population goes to infinity. So if they are in large population setting, they are learning a strategy profile that will behave well no matter the realization. And let me skip the proof to kind of stay in time. The last thing that I want to mention is that results that I've discussed so far are in the case where the only thing that's changing from time to time is the network of interaction. We were also interested in the question of what happened if agents are not always present. So in the idea of this open system, agents may actually decide to participate at game at time k with some probability p bar ii. So can we guarantee convergence even in this case? And what we show is that, again, you can guarantee convergence by looking at some type of gradient dynamics, with slightly caveat that, of course, if the agent is not present that day, so if PIIK is equal to 0, that means the agent is not showing up that day, then is not updating its strategy. Well, instead, when it's present, is updating its strategy, but with two slight modifications with respect to the scheme that we presented before. The first is that, of course, the interaction that are going to matter for the player that game are only interaction with players that are present. So instead of GK here, we have GK times PK, where PK is this diagonal of who is present, who is not that day. And then the other thing that we had to do to make things converge is to normalize the step size with respect to the expected probability of showing up. So like if agents are more likely to show up, they actually take shorter time steps, while instead if they show up not very often, they need to take larger steps. And then with this kind of modification to the gradient scheme, we do have similar result as before, that agents will convert to some strategy, and that strategy is the Nash equilibrium of the game played over the expected network, which is an epsilon Nash equilibrium for each of the stage games. Okay, so here I have some simulations to show that indeed we do converge, and this is kind of the suboptimality that we got. Let me skip to the conclusion because I'm running out of time. So here basically what we look at a general framework where we assume that the network of interaction is not given, but it's sampled from an underlying stochastic model. And we use this kind of framework to study both how a planner can understand strategic behavior when it doesn't have exact information about the network, as well as how agents can learn how to behave if the network changes in time according to this different realization from the underlying model. Okay, so that's all I wanted to say. Thank you so much for your attention. And if you have any questions, sorry, I only left 3 minutes for questions, but I'm happy to stay a bit over if that's allowed.
Thank you. Thank you very much, Francesca.